Suppose you're given a $5,000 inheritance with a condition that it must be put into a long-term trust for 10 years. One account offers a 6% interest rate that compounds monthly. The other offers a 5.5% continuously compounding interest rate. And we want to determine which of these is the better investment. So I'll say that in general, if you have comparable interest rates, or in particular if they are the same, you should expect continuously compounding interest to give you more money over time because, well, it compounds more. Where some things can throw that balance off a little bit, like in this case, it's not immediately obvious that the 6% is going to be enough to counteract that, and I'll say that the more times interest compounds, the closer it's going to get to matching because, well, larger numbers are closer to infinity, and continuously compounding interest means compounding an infinite number of times. But let's specifically take it in this case, where we have that initial investment in both cases is $5,000, and we're running it over t equals 10 years. Then, for the compound account, well, in particular, the monthly compounding account, we have that r is equal to 0.06 and n is equal to 12. So using this formula here, we have that our value following p times 1 plus r over n to the nt will in this case be 5,000 times 1 plus 0.06 divided by 12 raised to the 12 times 10, which is going to end up giving us an approximate value in this case of about $9,096.98. Pretty good deal. You basically double your money there over the course of 10 years. You probably want to do that even if you didn't have to put it in there. Meanwhile, for the continuously compounding account, what's going to happen there is really all we have to deal with is the interest rate, r equals 0.055, and for that, we're going to get that a equals PERT will be 5,000 times e raised to the 0.055 times 10. So it's really, really important here. I'm just going to stop before we get the computation to understand that e is not a variable. E is a very, very specific, very, very clunky, but very, very important number. One could make a very strong argument that the entire point of this section is to introduce e in its natural context and show a little bit about a natural exponential function. But I'll talk more about that in a second. So with this, if we plug that into the calculator, because you can't raise a number like e to any power in your head other than maybe 0 or 1, what you'd end up with is something like $8,666.27. So for this, that compounding interest rate with 6% was enough to make up the difference in the amount of times it compounds, because the first one would be the better investment. And so, now that we've seen a little bit about where e comes from and how we can use e, we'll talk about it in a little bit more of a specific context as the natural exponential function.